Okay, let's get started. Okay, so this is the fifth module of this class, but we still have many things to cover. So first, a quick walkthrough of homework 4. In homework 4, we have Crack Me 5, and also there is Maze 2. So everything else should be quite easy because we've already covered that in the class. So let's take a quick look of Crack Me 5. Crack Me 5 is Crack Me. So I'm going to show you the source code of Crack Me 5. You can see this is actually a very small program. We have a main function which checks if there are two command line arguments. If there are, it will just call the vol foo function. And the vol foo function, if you are not familiar with the syntax, so this is defining a local variable, which is a function pointer. So this is how you define a function pointer in C, and the function we are defining here doesn't take any arguments, and also it doesn't return any value, so it's void. So you can define other function pointer using the same way. You can put int here or whatever. So the local variable is initialized to 0 at the beginning. Then there is a memory copy from the second command line argument to directly overwrite this local variable. Then we will just call this function. So this is calling this function. As you can see here, this is how you call the function. So fp is the function pointer. You dereference the function pointer, then you put the parameter arguments here, which is we don't have any. So this is how you call a function using a function pointer. So as you can see here, so if we just put up whatever, just put some garbage here, then it will treat this garbage as an address and just jumps there. Then obviously it will generate segment fault for sure, right? So no matter what you put there, it will generate segment fault. So something interesting I want to show you here is the disassembly. You can see the other call functions we are familiar with is like call with an immediate number, and this is like calling a fixed address. Of course, sometimes it's calling an offset, but you can say here we are actually calling the value stored in the EAX. So this is something called an indirect call. Indirect call at the compiler time, you don't really know what is your target. So it's really hard to defend, especially if you deploy something like a control flow integrity. This is what you're trying to defend. So what I'm trying to show you in this example is sometimes you don't have to overflow the return address. You don't have to overflow the saved EBP. There are some local or global or even variables on the heap. They are pointers. In this case, this is a code pointer. This pointed to a function. So it's a function pointer or code pointer. So if you can overwrite that function pointer, you can still change the EIP. As long as you change EIP, the CPU will execute whatever code you want to execute. So that is Crack Me 5. So for Maze, you can say the problem is a little bit similar. I don't have the Maze binary with me, but you can see the problem is a little bit similar. The difference is we are jumping to we are giving the input, and the input where the CPU will jump to where our input is. So what your input there is actually treated as code, not treated machine code, not treated as address heap. So which means The vulnerability gives you an opportunity to run arbitrary code there. However, the arbitrary code is very small. It can only be 8 or 12 bytes. So you have to use it wisely. One way to do it is just to do a simple jump to a share code somewhere. You may have share code somewhere, then just jump it to the share code. The share code can do whatever you want. And there are many ways to do jump. You can do call, you can do a jump, you can push something to the stack and do a return. So all of those can change the EIP. So I checked your homework. It seems like everyone get it. I assume some of you probably search the internet and find some hints there. So I will double check if you understand every step there. If I get the feeling that you do not understand every step and just copy the exploit, you will not get the full score there. Okay, let's move to what we're going to discuss today.
Can I sneak in a question, Dr. Zhao, before?
Sure, sure.
So one thing I noticed was when I was trying to call like a direct call, like a program would for the first, my first iterations of just failing for hours at the maze 2, and I realized that there was like a ceiling on the stack in which I could no longer make direct calls after a certain address, and it wouldn't let me call straight into the environment variable.
It's probably not because of its stack. It's probably because the call function itself. Maybe there is a far call or near call.
I see.
There is an offset. You have to, or did you try to do like an indirect call? For example, put that in the EAX first, then call from the EAX?
I didn't. I only tried calls and jumps directly into where I had my my environment, and it would just kind of top out at an address that just sat sat somewhere else on the stack, and I couldn't increase it any further. And I was wondering if that was like a protection.
I don't think that's protection. I think that's probably the limitation of that instruction.
Okay.
There is a distance there. Yeah. The indirect call should be able to do the job, I think. Yeah.
Sure. In the end, I ended up calling an object that was already on the stack, and it picked up its memory location and went anywhere I wanted it to go. I didn't exactly understand why that changed, and it suddenly got so easy.
Okay.
But maybe it had to do with like canonical addresses being a certain range.
But we're doing 32 version, right? So 32 version doesn't really have that limitation. 64 version has that limitation.
Okay.
Yeah.
Yeah. Okay. I'll think more about it. Thanks, though.
Yeah. Okay. So next we are moving to what we're going to discuss today. Last week we saw that there are many other vectors we can use to inject share-code. We can put share-code in environment variable. We can also put share-code in command line arguments. And of course, in this case, we assume the stack is executable, and, which can be disabled in modern CPUs with that DEP feature. We also discussed, besides overwriting the return address directly, we can overwrite, save the EBP, and eventually hijack the control flow when the upper layer function returns. To bypass DEP, we also discussed we can use the return to libc attack, which we covered the 32-bit version, and we will revisit the 64-bit version for later. And today we are talking about several defense techniques. Actually, we're not going to talk about the stack count today, the sandbox, which is more like a kernel firewall for system calls. We're talking about next week. So today we're only covering 3 things. We will cover direct defense. We will cover stack cookies, Calorie, which is basically the same thing, 2 different names. And we will discuss one example. We will probably spend a lot of time on that example. We will see how to bypass stack cookies. Then we will actually talk about shadow stack first. So stack cookie is widely deployed. Shadow stack is kind of like very popular in academia because it's kind of like a very good balance between performance and security. It's not that secure. It is good, but the performance is not that bad. But I haven't seen it deployed in For example, GCC doesn't really have a built-in shadow stack implementation for x86. LLVM right now is working on one, but I don't think it's out yet. So let's talk about, before we talk about those, let me remind you that an attacker's ultimate goal usually is to take full control of the victim's computer. And this usually means that attacker can run arbitrary code on the victim computer. In some scenarios, this goal is too much to achieve. It's not necessary. For example, the attacker may just want to steal some information, steal a file on that system. Then obviously, if the attacker can achieve arbitrary code execution, then he can steal the file, but not necessarily. There are other vulnerabilities the attacker can exploit to steal the file without running arbitrary code there. So it depends on what the attacker wants to do. But in this class, we assume the attacker wants to run arbitrary code here. So usually to do so, the attacker needs to somehow hijack the legit control flow or redirect the control flow to his own code or reuse some code is already in the memory. So the point here is, as long as the attacker can change one code pointer, then eventually that code pointer is triggered, then the attacker can take the control. And there are so many things can be considered as a code pointer. For example, the return address is a code pointer. It directly points to the code where the function returned to. So it's a return pointer. The function pointer, what you did in crack me 5, is obviously also a code pointer. It points to somewhere you're going to execute code, even if at the beginning nothing is there. So there actually are many other code pointers, not necessarily on the stack. So far we have been showing things on the stack, but not always. On the stack, we have a return address. We have that base pointer EBP, saved EBP. That one is not a code pointer, but it will influence upper layer functions code pointer. Also, there is a set jump, long jump feature provided by C. So if you program in C or any other languages, usually there is a go to statement. So you can basically it's like a jump, unconditional jump inside a function. So that's go to. So set jump, long jump is a C feature offered at C library level. So the implementation is actually different for different architecture. So what set jump, long jump do is you can set jump, and it's a function call. It's not a system call. You can set jump, which will save current CPU registers into a variable. That variable you define it could be local, it could be global. Then your CPU keeps running. Then later, if you call the function long jump, which is also a function or a system call, then the CPU will go back to where you set jump. So obviously, to do that, set jump, long jump has to save the context, or maybe not the full context, but some of the context. I remember in x86, we're saving 6 or 8 registers onto the local variable. And one of the register is save the EIP. So you are saving the EIP to somewhere in the memory. So if you can override that, attacker can overwrite that. Save the EIP, obviously, it's a code pointer. So if you can override that, obviously, you can hijack the control flow. So set jump, long jump is available for C and C++. And also probably some of you program in C++. So how many of you program in C++? Raise your virtual hand if you program in C++, or physical hand if you want. Oh, oh yeah, you guys program in C++. Okay. So when you program in C++, in C++ you have something like a class, right? Class can inherit from other classes, and when you do that, um, you you can inherit another class with virtual functions. So to implement that, actually at the beginning of the class data structure, there is something called V tables. That's how compiler actually design these things. So the V table stands for the virtual function table. It's simply a list of function pointers. So your C class object can be on the stack, can on heap or any other places. And in that object, there are many function pointers. So if you can override any of those, obviously you can also hijack the control flow. There are some other code pointers we will cover later in this class. For example, the global offset table, the GOT, and the PRT. We will cover that because so far we have been discussing stack-based overflow, which is a sequential override. The vulnerability is introduced because of those functions, like memory copy, string copy, those functions, gets, right? So later, we will talk about other vulnerabilities that will allow you to override arbitrary memory locations. So when you can write arbitrary memory locations, then you can write any function pointers, code pointers in the memory. And for C programs, there are always global offset tables, at least for dynamically linked programs. They are there because your program is dynamically linked with libc, and at runtime, after the program is initialized, the linker or the loader has to fill in those addresses to tell the program where are those functions. For example, gets, fgets, where are those functions? So you can see that the risk is actually very high here. I mean, our binary, of course, for those ones, we will also discuss some defense for, you actually use a script of checksec. You can say checksec, let's see, let me get it real quick. So do I have checksec here? So we have checksec here, then we can do a grant me 5. Oh, I have to do final. Yes. So it will tell us what security features this program has. For this one is relocation. So this has full relocation. So this one is there to defeat GOT override. So which we will discover, we will talk about this on format string vulnerability, then stack canaries, and DEP, then this one is PIE, it's position independent. What's E? Oh, I think PI is position independent. So this one is related to address space layout randomization. Then I'm not really sure about what those two are. We're not going to cover those in this class. So you can see that our binary is at a very high risk. It's like we have a huge bottle of water, but the bottle is leaking anywhere. If you can find one vulnerability, then you can take full control of the computer. And also, besides those code pointers, there are other pointers we can leverage, not necessarily directly leverage to hijack the control flow of the program, but eventually it can help us. For example, at the very first vulnerability I showed you guys, the overflow one, that one we actually overflow a local variable. That local variable is related to conditional jump. It will influence the control flow. And that local variable, it's like kind of like a sensitive local variable. It's like authentication secret, something like that. And also there are like pointers used to read data. So if you can override that pointer, what will happen? You probably can read arbitrary location in the memory space. How could that be useful? This could be used for information leakage. Somehow you get some information you're not supposed to know, and that information can be used later for the next step of the attack. And also there could be a write pointer, not necessarily write to a code pointer, but it will allow you to write arbitrary memory. It can allow you to override a code pointer, for example. There is a variable on the somewhere memory, and that variable is a code pointer. And you have another vulnerability, which is a write pointer, which gives you the opportunity to overwrite anything you want, including the code pointer. So sometimes we just chain those vulnerabilities, exploits together, and achieve something you cannot achieve by just utilizing leveraging one vulnerability. Okay, so all of this can be called as buffer overflow, not necessarily stack-based buffer overflow. And there are two big categories of buffer overflow defense. The first category is what we call a full prevention of buffer overflow. It basically solves the buffer overflow problem directly. However, the cost of it could be very, very high, making it not practical for C or C++ programs. Because when you develop C and C++ programs, you just want those programs to be fast. And you don't want to make it slow. And those direct events usually is very, very slow. And then the other category of approaches are just we somehow make the exploit a little bit harder. Those are called an indirect approach. Usually they are not that useful, but they are effective. But the benefit of them is they are very fast. They are very cheap to implement. They are very cheap to run at runtime. And they are usually very simple in theory, and they are widely deployed in real world. So all the defenses you have seen so far, they are fall into this category. So the direct defense, they are very good in theory. Every time you find a paper talking about those, you will say it's very solid paper, usually published in programming language conferences, not necessarily in security conferences. But they are very expensive, so not really deployed in real world. So for example, base and bound check, which is used in other high-level programming languages like Java, Python, that is a direct approach. It basically prevents buffer overflow. When you use Java or when you use Python, you don't think about buffer overflow. However, if you want to do that for C and C++, it's doable, but too expensive. So today we will talk about stack cookie. We'll spend a lot of time on stack cookie, and you can see it's a very, very simple approach. So simple that high schooler can understand, and at the same time, it's so effective. We have been using it for more than 15 years, and it can sometimes prevent overwriting return address on the stack, but it's not perfect. So today we will actually spend a lot of time on how to bypass stack cookies for one cases under one scenario, and also data execution prevention. The DEP is also indirect defense. It can prevent using share-code on stack or other writable memory regions. However, we can easily bypass that. We can use return to libc or other approaches to bypass it. We'll talk a little bit about what is base and bound check. So a lot of high-level programming languages provide this feature, and it's transparent to developers. So if you develop in Java, you don't really think about this. So the problem we are solving here is called spatial memory safety problem, because you overwrite to a buffer which you are not supposed to access or write to. So it's a spatial problem. It's not a temporal problem, right? So in those, so here I'm still using C as an example. So for example, whenever a programmer defines a pointer, for example, we have a char star A here, then the compiler can inject two more pointers there. One is the base of A and also the upper bound of A and the lower bound of A. For example, we want to use create A on heap. Then what do? We do a malloc, and we do a malloc of 512 bytes here. Then for this variable, the pointer A, we have a base for it. It's basically the beginning of A. Then the upper bound is A plus 512. So whenever in your program there is a dereference of A, access based on A, then we are going to check if it is in the bound, if it's between the base and the bound. That's it. Sounds very simple, but since it could be a little bit complicated, especially the pointers can be assigned to others, right? So this is kind of like an alias problem. There could be many different pointers. They are pointing to the same thing or things are related. So this is more like an alias problem in program analysis language or programming language error, they call it alias. So for example, here we have a pointer B. B is assigned to A in its definition. So B is supposed to have the same range as A. So when you dereference B, it should be the same as you dereference A. You should not go out of bound. But sometimes things could get a little bit trickier. For example, C is another pointer. C is not directly assigned to B. Instead, it's pointing to the middle of the array of B, if we consider B as an array. In this case, the C space should be the same as A and B space, and C bound should be the same as A and B bounds. Otherwise, this approach doesn't work. So this is basically how this approach works. And you can see that if you want to implement like this, something like this, you need to make changes to the compiler. Every time you define a new pointer, you need to create two more pointers. Every time you have an assignment, you need to two more assignment for the base and bound for the new pointer. And also, anytime you have a div reference, for example, here you have probably have div reference or something, then you need to check if that is valid. So the overhead of this is it's quite bad. You can imagine the cost is very high. Whenever you store a pointer, under the hood there will be two more pointers. Whenever there is an assignment under the hood, there will be two more assignments. So if this maps to one, sometimes it maps to multiple instructions, then you have to time that 3 times, times 3, basically. That's the cost. And also, if there is any dereference like this, you have a C, you want to get the ith element of C, this is a dereference. Whenever there is a dereference, you also need to check at runtime. So this is basically adding 2 more checks. So this is how most programming languages, high-level programming languages, Java and Python, implement this. And for C, we can do it, but usually people don't want to do it because it's too costly. For example, this is a PLDI paper in 2009. So PLDI is the top value for programming languages. It's called a programming language design, what's I? I'm not sure. And implementation, I guess, probably programming language design and implementation. So that's the top conference, one of the top conference in programming languages. And you can see this is basically a paper implements something we just discussed for C language. So you can imagine in the papers there are many theoretical proof that this is secure However, you don't really see something like this used in real world. GCC is not using this, LLVM is not using this. It's not very practical. Then there are also other approaches. For example, this is another paper at the same year from another top conference, S-Plots. So this is a conference actually I like very much because this conference is at the boundary of hardware and software. So it's basically called architecture support for maybe architecture and programming language support for system. I'm not sure. So anyway, it's a conference at the boundary of software and hardware. It has many architecture things here and also many system things. So this paper, are they from the same group? Oh yeah, see. So those two are probably professors. So in this paper, they discussed how they can make the softbound approach a little bit faster by utilizing some hardware features. But still, even they can make it quite faster, it's still very costly, so we do not see them in real world. So we already talked about DEP. Today we will start with shadow stacks, then we will go to stack Calorie. Like I said, shadow stack is still a hot topic in system security for academia. Every year, we still see many papers implementing shadow stack, discussing about shadow stack for different architecture, different environment. This year, I remember there is the paper for shadow stack for ARM devices. It was from University of Rochester. And also I had a student who interned with Qualcomm at San Diego. And what he was doing is he was implementing shadow stack for ARM trust zone trusted applications. So shadow stack is still a hot topic, even though it seems very simple, but still a hot topic. Unfortunately, GCC, LLVM, neither of them right now support shadow stack on x86. So I don't really have any actual code to show you today. So I don't really have a compiler to show you what's the code with shadow stack will look like. I will only show you the proof of concept code from the papers. But we will discuss the principle of it and how it can be implemented. So the purpose of shadow stack is to protect the return address saved on the stack from tampering. So I took this picture from a 2015 Asia CCS paper. So Asia CCS is actually also a very good system security conference. You probably know the top 4 security conferences for security guys are IEEE Security and Privacy. That's the most difficult one to get in. Usually the acceptance rate is like 10% or something. I only have one paper here after working on security for 10 years or more. It's just extremely difficult to get in. Then we have Usenix security. Usenix security is like my favorite. I have many papers here. Then we have ACM, CCS, and also NDSS. From the name, you can see that this one is called Asia CCS. So it's related to CCS. They are both organized by ACM. And this one actually is always hosted in Asia. So it's a good conference. I consider it a tier 2 conference. So from this paper published only 4 years ago, 5 years ago, you can see in the middle of this figure, we have a stack with 4 nested function calls. They are joining the stack like how we are joining it. So this is high address here. The bottom is a low address. So let's say function 1, function 0, we'll call function 1. That's why the return address here is R0. Then function 1 will call function 2. So the stack keep going this way. Then we have parameters. So this is obviously 32-bit version. We have parameters, return address, and saved EBP for each function there. So this is what our stack look like. This is what we have been looking at for the last several weeks, right? So because of the software vulnerability of any of those programs, then attacker will be able to override everything above this. So there's a risk some of those return addresses could be overwritten. So the idea of a shadow stack is, in addition to save those return addresses onto the stack, onto the original stack like this, we save another copy of those addresses in a safer place. Of course, there is another issue is how can you find a safer place? How do you know that the other place is safer? As shown in the left-hand side of this figure, we are using something called GS here. GS is another general register, and we actually will talk about this later when we talk about Calorie. So right now you just treat this as a memory location. So at this memory location, we assume this memory location is safe. We will save all the return addresses, save another copy of it. So what is the implication of this? Even though the function has a vulnerability, let's say R2, function 2 has a vulnerability. The local variable of R2 are here. So it will be able to override all of this. However, it can only override all of this. It cannot override here because stack-based buffer overflow is a sequential overflow. You cannot override arbitrary address in the memory you want. You can only override the sequential address here. So even if you override here, this shadow stack here is still safe. Then when you returns, instead of using the value at the return address on the original stack, you will use the return address on the shadow stack. So that's basically the idea. It's very simple. We will look at the implementation in a minute. But however, you can see this approach is not perfect. Okay. The shadow stack approach, we are several problems here. First, how can you make sure the shadow stack itself is safe? Of course, that's a totally different issue. Second, what if the attack, the override happens before you save the shadow stack, you save the return address to the shadow stack? What if what you save to the shadow stack is already something compromised? Third, there are so many things on the stack, and those things will influence your program's control flow, or influence your program's data flow, like local variables, like saved EBPs. But if you are only saving the saved address, the return address, it doesn't mean your program can run normally. Probably your program can never return, right? Can still has some bugs, something will crash anyway. But of course, to solve the last problem, what you can do is, the worst case, you just save everything on a shadow stack. The shadow stack will be the same as the main stack, but you can see the cost will be too high. It's not useful. Okay, so let's take a look at how we implement this shadow stack. So what we're going to do is we're going to change the prologue and the epilogue of a function you want to protect. And if you want to change that, obviously you change this at the compiler. So the developer doesn't have to do anything. As a developer, where the source code doesn't have to be changed, then the compiler we're just adding those instructions. You can see there are not many instructions. Here we say we are adding like 4 or 5. So the prologue we're adding like 4 instructions. The epilogue probably is also 4 because the return is the original return. So the prologue we will end before the original prologue. So original prologue is like we push EBP, move EBP, ESP, those two. And also we say if there is a stack alignment, we say last week's correct me forward. So if there is a stack alignment, then there will be something to align the stack. There are several instructions. So all of this should be, if we want to add this, all of this should happen even before that. So let's see what we do here. This is at the very beginning of this function. So at the very beginning of function, what do we have? Well, how did we get here? We get here because the upper layer function executes the call instruction, right? That's how we get here. So at this point, the ESP, the pointer, points to the return address, which is the return address is pushed there by the call function, and the ESP points to there. Then what we do is, this is another variable. Right now, you just consider this is a variable somewhere in memory. The actual address of this doesn't really matter. How do we get the variable? It's we use GS column 108, and usually this is a fixed one because we use a different address for different purposes. Then we subtract it for. So this one somehow act like our shadow stack pointer. So that's why it's not a register. So the stack pointer, the ESP is a register. Here we just have a local variable. We use it as a shadow stack pointer. So that's why we call it SSP, shadow stack pointer. And we subtract it for because we're going to push something there. Then we move the value of it, the value of it to EAX. So we know where our shadow stack top is. Then we move whatever our ESP points to. So our ESP points to the return address. Of course, at this point, like I said beginning, we assume the return address at this point is not compromised. So if at this point the return address is already compromised, then this approach doesn't really help. So the return address is not compromised, then we move that return address to the register ECX. So what's next to do? We're going to move the return address to the shadow stack. And the shadow stack, the address is in EAX. So those are the 4 instructions we need to add at the beginning of the function we want to protect. And obviously we cannot combine those 2 instructions because this one is a memory, this one is memory, and there is no instruction to move data directly from memory to memory. So that's why we have 2 instructions here. So after this, we pushed a new return address. We made a copy of the return address on the original stack to the new stack. That's it. That's so simple. So for the epilogue, obviously, what we want to do, we just want to, we can check if they match. If they don't match, we just exit. That's one of the approaches. The second approach is we can overwrite the original overwrite the original stack. So this is the original stack, no returns. The return address R3 will overwrite the original one. So we don't even need to check. We trust this one. We just overwrite this. So this is the code for the overwrite option. So first, we move the shadow stack pointer to ECX. Then we add the shadow stack pointer 4, so increment that. Then we move the return address on the shadow stack to EDX. So EDX right now has the return address from shadow stack. Then we move that return address from shadow stack to where ESP points to. So we override. We don't really care if the value ESP points to right now is overwritten. We don't care. We just override it again. then we do return. So you can say because of this, this piece of code has to be last ones to execute in a function. And those has to be the first one to be executing the function. Depends on where the ESP points to. Other things don't really matter. What matters is what ESP points to. This piece of code requires that ESP points to return address. The same thing here. This one requires ESP points to return address. So if you do not put the code at the very beginning, then you have to adjust this code a little bit. So this is basically how shadow stack works. And this is something now we call traditional shadow stack. This is, I'm not really sure who proposed the shadow stack. I don't think it's from a paper. So we don't really have a paper for the original, but this is a traditional one. So here is another approach. Instead of overwrite, we can just check those addresses. If they don't match, we just exit. We just crash the program. It's the same thing. We move the return address on shadow stack to EDX. Then we just compare EDX with whatever stored on the original stack. If jump non-zero means they do not equal. If they are not the same, we just hold the program. That's it. If they are the same, then we return. So this is basically how we implement shadow stack. So if we count the overhead here, you can say we have at least 6 more instructions. I'm talking about consider there's no attack. If there is attack, then whatever cost is worthwhile. So I'm talking about if there's no attack, for each function, we're talking about at least 6 or actually more, maybe 8 instructions there. Then in those instructions, some of them are memory moves. For example, this one, we're moving, even this one, we're moving from memory to register another one. So those are 3 moves. There are actually 3 moves. So there are actually more than 2. How did I get those numbers? I count them. I don't know what I was thinking there. Anyway, so there are many memory moves, and memory moves are kind of slow because the CPU is talking with memory. You have to go through the bus, so it's kind of slow. Then there is also memory compare, conditional jump. So the cost is usually depends on a lot of things, right? If your function is huge, your function has 200, 300 instructions, then the cost is low. You're just adding 8 instructions there, the cost is low. But if your function is small, then the cost is very high. Your function is only 10 instructions, and you are adding 8 there, then the cost is very high. On average, people say the cost of this traditional shadow stack is kind of like 10%, depending on average means we use a lot of programs, we compile them. Some programs we usually use, we compile them, then we measure the performance, then the cost is like 10%. Then another way to implement shadow stack, which was proposed in this Asia CCS 15 paper, is something called parallel shadow stack. It doesn't save anything more. It still just saves the return addresses. And the advantage of this is it's much faster. So here we say we're adding 8 instructions, 6 moves. What is this new implementation of parallel shadow stack is like we're only using 4 instructions. So it's just using some tricks. This is not like a very hard math to understand. They just use some tricks here. So let's take a look how they do it. The idea is here we have the main original stack. Instead of having go through this complicated pointers, everything, we set up a fixed address, fixed offset from the main stack and use that as a shadow stack. So if the return address is saved at, let's say, address 10. Then our shadow stack, it will save the return address like, let's say if there's a 100 offset, will be 110. And we are saving all those addresses at offset plus their original address. Then obviously, all the bytes memory locations between them will be wasted, but doesn't matter. We're not going to use them. We're making things much faster. And the implementation of this is much simpler, as you can see. So the prologue for this one is only 2 instructions. Instead of this 4 instruction here, we're just doing 2 instructions. And the 2 instructions will be this piece of code is still at the beginning of the program, the function. So ESP points to what? The ESP points to the return address. So the first instruction is a pop instruction, but we're not popping. We're directly popping something from memory to memory. The source of the popping is not defined here, right? When we do pop, the source of popping is always what ESP points to, right? So we're popping it to the current ESP's location plus this fixed offset. This is fixed. So after this instruction, what happens is the value of ESP will increment 4 bytes. It will actually, after this instruction, it will actually, the ESP will not point to a return address anymore. It will point to 4 bytes higher than that. However, the return address will have another copy, which is at the ESP plus this address. And that is where our shadow stack is. Then after this pop, we need to fix the real stack pointer. We need to make the stack balance. And that's easy. We just subtract ESP4. And the return address is not changed. Those 2 instructions will not change whatever on the main stack. We're just moving the stack pointers. So with those 2 instructions and only 1 memory move, we achieved a shadow stack. We achieved shadow stack here. So compared to what we did before, we have fewer instructions. We have fewer numbers of data movements. And the epilogue for it is just the same. We first add ESP4. Then, so the ESP at the beginning, at this point, points to a return address, right? The return address could be compromised. Then we add 4 bytes to it. Now it points to the return address plus 4. Then we push what we have on the shadow stack back to where ESP is. So after that, ESP will decrement 4 bytes, overwrite the original that could be compromised the return address. So this is how it works. That's very simple. And they argue that this is kind of like the optimal way to implement shadow stack. They do not see any other way to implement shadow stack in at least on this architecture. So the overhead for traditional shadow stack is like 10%. For this new type of shadow stack, they claim that overhead could be as low as 3.5%. So that's basically what shadow stack is. Any questions for shadow stack? Okay, everyone's good? Okay. Now we are moving to interesting topic, which is stack cookies. And for stack cookies, we do have real-world implementations. So GCC, LLVM, they all implement stack cookies. So we will be able to see some real-world examples, real-world deployment, and we will also see how to bypass it. So Stack cookies are also called canaries. So basically, canary is a bird. If you are miners, you bring a bird with you to underground. If something bad happens, for example, some gas leakage, which human cannot detect, but the canary uh, will be killed because of that, then the miners know it's time for them to go up. So that's why it's also called a canary. So, so canary is actually specific to protect against the sequential stack overflow. Kind of like this one is different from shadow stack. For example, we have a arbitrary memory write vulnerability. For shadow stack, let's say we are in function 2. And function 2 has a vulnerability that we can overwrite any address. Then as an attacker, we may choose to overwrite the return address R1 here. If we overwrite that, shadow stack will be able to detect that. And shadow stack will be able to defeat that because that the original address was saved in shadow stack. However, canary is different. Canary is like we place something in the middle. If we overwrite, if we can override arbitrary memory, then we can skip this one. We do not do a sequential override. We directly override this, and canary will not be able to detect it. However, canary is still a very useful, effective approach. So the idea of a canary was first proposed in this 1908 Unix security paper. The title was Stack Guard, Automatic Adaptive Detection and Prevention of Buffer Overflow Attacks. In this paper, they actually proposed 2 approaches. One is canary. Another one is much more expensive, much more complicated. But right now, when people talk about this paper, people think about canary. As a homework, you will read this paper. You can see the other approach is very expensive. No one actually talks about it anymore. So the work was actually done probably in 1997 something. The paper was published in 1998. And 15 years later in 2013, this paper won the Test of Time Paper Award in Unix Security. So every year at Unix Security, and I think the Big Four, they all have this. Every year, they gave out one Test of Time Paper Award, sometimes probably 2, to honor one of the papers published 10 years ago or 15 years ago, based on its influence in academia and also industry. So because this is like 10 years and 15 years later, you can say how hard it is to get an award like this. And it shows that what kind of influence this paper has brought to academia and both academia and industry. However, you can say the idea of this paper is extremely simple. So actually today I saw someone comparing what our system guys or security guys do to what those machine learning guys do. A lot of what we're doing is like we have an idea, we spend 3,000 hours, several guys together to implement that idea. But that idea itself is understandable by everyone. The math we are using is like high school or middle school math, not much math. So far, we are not really, besides addition and subtraction, what math are we using? We're not using much math, right? But a lot of dirty work, we do a lot of coding, we do a lot of evaluation. So every time we publish a paper, when we have the idea at the point to where we publish a paper, usually it will take sometimes 2 years. Then for those machine learning guys, sometimes they have a very good intuition of a math. Then they prove it. Then one guy spent 200 hours can finish a project. and they can publish in their top conferences. And it may take them 3 to 6 months to publish in top conferences. So there's much difference between system guys do things and theory guys do things. So in short, stack guard or canary or stack cookies is a compiler technique that attempts to eliminate buffer overflow vulnerabilities, sequential buffer overflow vulnerability. But obviously, it cannot, as I explained. This is an indirect defense. It cannot eliminate the problem. There are several benefits of this. There is no source code change needed. The developer doesn't have to change anything. Everything is done by the compiler. The compiler will automatically patch the to-be protected function prologue and epilogue. In the prologue, the code will just push one additional value onto the stack. And the additional value is called the cookie or the canary. And that additional value for 32-bit version, the program is just a 32-bit, 4 bytes. For 64-bit version, it's 64 bits. So in the epilogue, similar to what we did in shadow stack, the code will just simply check if the saved canary on the stack has been changed. Since the buffer overflow we have seen so far are introduced by unsafe functions like fgets, gets, memory copy, string copy. So they can only copy data sequentially to the destination if the destination is a return address or saved EBP. The simple observation here is, or what canaries rely on is, if the attacker has to override the return address on the stack, then he or she has to override the canary as well. Then if they override the canary, then we can detect the attack. Obviously, there are many ways to bypass this. First of all, like I said just now, this is not effective against arbitrary write vulnerability, which we were discussing in format string vulnerability, or if you have any write pointer, you can do that. You can control any write pointer, you can do that. That cannot be defeated using this canary. Okay, we will use overflow return 4 as example. We have seen this code many times. Very simple code. The main function calls the variable function. We don't really check the command argument, and the variable function at a C level has a 30 bytes buffer. Then it takes input from standard std_in, and you can input as many bytes as you want. And this is where the buffer overflow is. We have seen this many times. Let's take a look one more time here. Where are we going? We're going to overflow return 4. So I actually compile it. I have a makefile here. It will compile it into different programs. So last week, you guys, you worked on this version. Yeah, no execution, which is a DEP version. So this week we will take a look at this DEP version and also with Canary. So which one is it?
I think NC is with Canary, without Canary.
NC.
So no Canary.
Yeah. Oh yeah. So we're going to do this one, right? So yeah, this one is the safest one basically. So OR4NX. Yeah, this one is actually the safest one. So this one is like the stack is not executable, and also there is canary. Yeah, this is a version. So if we do check stack, let's do a check stack. Check stack file OR. Yeah, so this one is a safe one. This one we have all the security enabled. So if we take a look at this code here. Okay. Yeah. So if we take a look at this code, we're going to look at the Overflow function. So this is a variable function. So we haven't talked about this part yet. This is related to the position independent code, but we will talk about this later. So let's say we have gets here. Okay, so here, yeah, I should go back to my slides actually. Better to have this on my slide. So, okay, this is the version we don't have Calorie, which we are familiar with. We have gets here. We have this local variable buffer at EBP minus 30 in hex. That's it. Then we have this Calorie version. The only difference is those 7 instructions. That's what we add for Calorie. So let's take a look at those instructions. The first instruction is move GS column 14 to ECX. Like I said, at this point, we don't care what this is. What I can tell you is this is some memory location. We will actually talk about this later. So at this memory location, there is some value, obviously. Then that value is Calorie. And that value is generated when the program starts. When the program is loaded, when the program was initialized, that's where we put the Calorie. And we move that value to ECX, which means 2 things. First, if you run this program multiple times, the Calorie will be different each time. That's the first thing. The second, inside one process, the Calorie is always the same. So all the functions, they will use the same Calorie value. That's the second thing. The third one is, because this is done, this value is generated. It's like a random value. I will say later, it's not that random. It's a random value generated at when the program is created. So if this program fork itself, make another copy of itself, you use a system fork, this value will not be changed. Because when you fork, it will copy everything, all the context. And this value is not changed. So if a program forks itself many, many times, it gives us more opportunities to hack this, right? So we move the Calorie from this address to ECX. Then we move this ECX to where? To the stack, to EBP minus C. Then we exclusive OR ECX. So basically, we want to make the value 0. So ECX has a Calorie, then we just flush it out to 0. So this is how we set up the Calorie. And the Calorie, for at least for GCC, it has this fixed address, which is EBP minus C. Okay. So EBP points to save the EBP. EBP plus 4 is a return address. Higher than that is arguments. And we said before, some locations lower than EBP probably is local variables. But now with this compiler flag, with this stack protector Calorie, we are actually saving the Calorie at EBP minus C. That's where our Calorie is. Everything lower than at that address will be local variables. Any questions here? Good, okay. Then after that, we do whatever we want to do, the program logic. Then before we return, this is what we're going to do, okay? First, we move the Calorie number on the stack back to ECX. Then we compare the value of ECX, the value in ECX, with whatever is at GS14. That's original Calorie value. We can do a compare. We do exclusive OR, doesn't really matter. Then if they equal, we will jump to this place. So this is like the epilogue of the original program. If they do not equal, we will call this function stack check fail local. So basically, if they do not match, we will just exit. So it's just as simple as that. So let's do a simple demo to see how this works. We have this variable program. It takes, how many bytes we're talking about? We're talking about another bytes, right? So let's do Python here.
Quick question.
Yeah.
At which point does the canary gets generated again? I guess you said at the start of the function, does this like function have special function to generate it, or how does it do it?
It is actually generated when this program is created. It was generated once at the initialization of this process, not a program process. Sorry. Yeah.
Okay, so the function. Oh, sorry. The program itself, it generates it when it starts. It's not like something passes at that value.
Well, I think it's the loader generates that random value, and that value is passed to the, actually this address, the GS, this is, I will talk about it in a moment. This address is something called the thread local storage, and the loader will probably put that canary value at this storage address, and all the programs will be able to, all the functions will be able to access this. So see, here we're actually accessing this memory location. We're reading it, but we are not changing the value of GS. We cannot change that. The program cannot change the value of GS. GS is kind of like a sensitive register here. Only the kernel can change the value of GS. If the program wants to change that, the program has to call a special system call to do so. Does that make sense?
Yeah.
Okay.
So in a program, if there are multiple functions,
yeah,
all the functions will use the same value.
Exactly. Yeah, we will say that in a moment. They will use the same value because they are all using the value from here. Yeah, but note that, I mean, this is the implementation of GCC and our current canary. Obviously, if you want to do a more fine-grained version, a better version, you can have different canaries, right? But you need to consider the performance, the cost. I'm just saying the current implementation of GCC, all the functions, not only all the functions, the process, right, has only one canary value, and this value is generated at initialization. So if this program fork itself, it will not even be changed. Yeah, that's how we are going to attack it later. You will see. Yeah. So here, what is the location we're looking at? So the buffer is at 34. What is 34? What is the decimal?
52.
52. Okay.
I think so.
Okay. So 52. So when we do 52, we're not overriding anything. Oh no, we are overriding. We're overriding the canary actually. Right. Okay. I think I have one more slide for that. Yeah. By the way, if you don't remember what GS is a general register here. It used to be it's called segment registers. Used to be segment registers. Right now they're called segment selectors. I think selector registers, and it's not easy to explain how they are used. It's not, you can notice the syntax here. Even the syntax is different from what we're familiar with, right? We never use a EAX like this, so it's a little bit different. We just treat this as like, when we do this, we're getting 4 bytes from some memory location. So when we can compare those stack layout, so for the version without canary, we have buffer, and from disassembly, we can say, from here, we can say the buffer is at EBX minus 30. However, with this version, so the buffer is actually at EBX minus 34. So this is where our buffer is. However, not everything is our buffer. Our canary is actually at EBP minus C. It's always here. You know, if you use GCC, it's always here. The canary is always here. So which means the beginning of buffer to the canary is actually 40 bytes. It's actually 40 bytes. So if we put 39 bytes here, we will not overwrite anything. If we put 39 bytes here, we're not overwriting the canary. But if we put 40 bytes here, yeah, 40 bytes should be okay as well. 40 bytes here, then we are, if we overwrite 40 bytes, then we will fully overwrite this part. Even though the buffer at the C level is 30 bytes, we overwrite 10 more bytes, but we are not touching the canary, right? So canary is not changed, so it cannot detect we are doing buffer overflow. If we do 41 bytes, okay, we're actually not changing the saved EBP. We're not changing the return address. We're only changing the 1 byte of canary. Then what will happen? They will be able to detect that there is a buffer overflow. So it will print out this message, stack smashing detected. And it will just, the program will be aborted. So this is exactly what this function does. This function is stack check fail local. So this function will print out this message and just abort. So actually, we're not doing anything super dangerous, right? We're not, even if you do more, the same thing. So you overwrite 41 bytes or you overwrite 145 bytes, will be the same thing. So basically, we change the canary. That's how that's how they detect the buffer overflow. If we check the 64 version of this, you can see things are quite similar. There are only 2 differences. But first of all, the size of a canary is different. The size of canary is 8 bytes in this case. And also, we're not getting the canary from GS column 14 anymore. We're getting canary from FS column 28 in hex. So this is a canary. So previous it was GS 14, now it's FS 28. That's only because the 32-bit version, we are using GS to point to the thread local storage. And 64-bit version, we are using FS to point to the thread local storage. And obviously in that thread local storage, we save all kinds of things, and some of them are pointers. Obviously the pointer size will be different. That's why the offset is also different. So we did a quick demo there. Let's say we can use strace. Let's see. And let's see if we want to, let's say we use strace to see what's going on here. Let's say we can do 41. We put this into something called exploit. So we can do a strace. Then we do a strace OR for an X. We put exploit here. The reason I do this is if I put an strace at the beginning of this command, we're going to strace Python. I don't want to do that. I only want to strace this program with this input. Then we can say here, when I do this, you notice that my Ubuntu find out there is a vulnerability, ask me if I want to send out this. So if you check here, first there is a system call you can pay attention to, is this one called a set thread area. So this is a system call to set up the thread local storage. I think most programs will use this anyway, but this is related to our, because our canary is also set somewhere there. Then the system call, what important is, so we have read here and we have write. So when we read, we trigger the problem, then the stack fail local function will print out there is a stack smash detected. Then it will just kill the program. So this is what happens. So if we check the 64-bit version, let's see what is the address here. 64-bit version. The address is actually 30 in this case. 30 is no. So it should be 30. Do I have an answer for it? 30 minus 8, right? So 30 is 40. 30 is 40. 48. So it's, oh, it's actually the same, 40 bytes. So if we're doing the 64-bit version, the 40 bytes we will not override canary, so everything is good. If we put one more byte there, it will override the canary. So you can see this is basically how stack canary works. If we debug this program, we can see more clear what's going on. We debug this program. We set a breakpoint at then we run this program. So when we run this, so let's check the value of the canary. So let's say run over here. Okay. After this one, we are getting the value of canary from this address. It's in ECX. Let's say what's here. What's in ECX? So ECX, we have this value, CE665 96, then 00. So this is our canary. Yeah, let's just set a breakpoint here. It will be better. So let's set a breakpoint here. Then if we rerun this program, we run this program. Now we're here. Then let's check the value again. So see, the value is different this time. It's 42883800. Okay, do you notice something? If we run this again, continue, this is a different value. Do you notice something here?
I see one more run.
Yep, let's do one more. Let's run, continue, yep, one more run.
00 suffixes on these?
Okay. Yes, the least significant byte is always 00 on Linux. It's always 00. So it's not like a full 4 bytes randomness. It's only 3 bytes randomness here. So, but why do they put 00 there? Think why do they put 00? Actually, this one we got lucky. We have 2 zeros. The leading bytes is also 00. But that one is just random. We just it's a coincidence. So this one is also least significant bytes is 00. Okay, let's do a check the other version, the 64-bit version of this. So we go through. We just want one piece of sample. That's very well. Okay, we just want. Yeah, so RAX is our canary in this case. Breakpoint here. Just run it. What's going on? Cannot access memory. Oh, this one. Oh, that's not a real address. That's not a real address. That's partition independent code. Did I type it wrong? What's going on? Did I type anything wrong here? Looks correct to me. Okay, so we can move through. Okay, so now we run this. Yeah, so we didn't have a correct address there. That's why. Now we have this address. We set a breakpoint here. Okay, if we rerun this, we continue. Our canary is in RAX, and you can see the least significant byte is always 0. And this is our canary right now. If we rerun this again, we get a different canary, right? However, the last byte is still 0. So any idea here why to have a 0?
I have the same guess as Charlie had in the chat, but it looks like it's acting like a pseudo string that has like a null terminator at the very end. That's
exactly. That's why we have a 0. Let me turn on my light first.
Sorry, I didn't say anything because I'm meeting.
Exactly. That's why we put a 0, 0, because for vulnerable functions like a string copy, something like that, you cannot really put a 0, 0. So you will not be able to overwrite this. That's a reason. Okay, let's go back to the slide. Go back to the slide. Where are we? We'll look at this one. Okay, so if we, oh, I see what I was doing. I was doing the stack canary, then I copied the overhead to stack shadow. Then I thought I already did it. So that's why. So the canary one you can see for 32-bit version, it's like we have 6 more instructions and 2 more moves. Actually, more than 3 more moves. Three moves and a conditional jump. So that is a cost. So the cost is acceptable, not terrible, but it probably will be like 8-9% of overhead cost, I think. Then the next question we want to talk about is what is this? What is this GS14? What is this FS28? And also how this canary value is generated. So first of all, what is the syntax? The syntax is weird. We haven't seen anything like this. In short, I would say applications or long kernel programs in Linux, they will make use the FS register and also GS register to access per thread context. And that per thread context including something called TLS, thread local storage. So it could be some variables that is local to a specific thread. And the FSGS, they are obviously registers. They are general registers, but they cannot be changed by applications directly. Only the kernel can change this. And also we saw that in that move instruction there, we're only reading the value of GS. We're not changing it. So if you go to the debugger, you can see we can actually print out the value of GS because we are. So this is 32 version or 60. Oh, this is 64 version. Okay, we can print out the value of FS. Oh, sorry. So this one, yeah, we can print out the value of FS. It's just a 0. But that value is not the value of the memory location. It's actually a selector. It maps to another kernel data structure. From their kernel data structure, they will get the actual address. It's quite complicated there. So only the kernel privilege code can change GSFS. There is also the GDB I installed for you guys. we have another plugin called PungGDB, and this plugin, there is a command TRS. I probably installed it wrong, so I will send you guys new instructions to how to install that in your virtual machine. But here, if we type TSS, we can get the actual address of this thread local storage structure. And remember, this is what this is 64-bit version. So this address plus 28, right? Plus 28. That will be our canary. Why we cannot access it? Did I do anything wrong here? Oh yeah, without the stop. So this should be our canary. See, this is our canary. It's exactly the same as what we have RAX. So this is where the canary actually stored at the TRS plus 28. So this is the 64 version. If we check the 32 version, let's do just here, just to run this. When we get the canary, where do we get the canary? Now we have the canary in ECX, and we use the command TRS. We can get the address of TRS, and then we can just examine this. I used the GX before for the 64 version because G means giant, which means a 64 version. For 64 version, 62-bit version, we just use W, means word, I guess. That means W. Then we plus 14, that's where our canary is. So see, our canary is this value, which is stored in ECX. See, that's the same value. So this value is generated when the program is created. And all the functions go to that place to retrieve that value. Okay, so there are many different types of canaries. So the paper I just showed you, the Unix security paper, is actually the original paper in Canary, but obviously there are many different approaches, projects work on that after that. The original idea is just to have a random canary. It's a pure random number when the program is loaded. Then there are other ideas. It's like, for example, we use that random value to do exclusive OR with the return address. It's like we somehow embedded the return address information into that what we store there. That's another approach. Another approach is we just put a fixed canary there, put all zero there. And that should be able to stop something like a string copy. Yeah, basically just string copy because it doesn't really stop gets or fgets. Gets can do zeros, right? Then there is another way is another fixed canary. Is but of course those are fixed canaries. A fixed canary like one example is something like this. It's called a terminator canary. There are 0 to terminate a string copy. There are nil line, OA is nil line to terminate gets. There is OD to terminate carriage return, FF to terminate form feed. I'm not really sure what is form feed actually, but this is called a terminate canary. Even though they are fixed, they can stop some kind of attempt, right? So those are the terminated canaries and different types of canaries. But obviously, random canary is still quite safe. This slide, I want you to know a little bit about the evolution of canary. It was first introduced in 1998. Those authors of that paper, they developed GCC patches. However, GCC never accepted their patch as official GCC into the GCC tree. So they didn't make it to the GCC tree. Then from 2001 to 2005, IBM developed something called the Properties. We're going to see that in a moment. That one does not only add a canary, it also rearrange buffers. So we will take that, take a look through it. Then 8 years ago, Google actually implemented something called Stack Protector Strong Flag. So you see, what I'm using is a Stack Protector flag, or you can use a Stack Protector All flag. The Stack Protector All flag will protect all the functions. What I'm going to show you here, the default one is a Stack Pointer flag, and that flag you can see if we do JDump. If you compare the main function, and the Volfo function, you see what are the differences here. The Volfo function, they actually get canary from GS14, but the main function didn't do that. The main function doesn't have a canary here. That's because the GCC flag I'm going there is a stack protector. It will not generate a canary for all the functions. It has some rules to generate canaries for specific functions. But if you use for performance reasons, if you put a canary on all the programs, then all the functions, you will make them slower. So if you use the stack protector or flag, then all the function will be protected, including the main function we saw, it will be protected. Then Google in 2012, they designed something called a Stack Protector Strong, which balance between security and performance. So this flag protects more kinds of vulnerable functions than Stack Protector does, but not every function like Stack Protector All does. And this one is available for GCC for a while. And most packages in Ubuntu right now are compiled with Stack Protector flag. And Arch Linux, some people like Arch Linux, and Arch Linux also use Stack Protector since 2011 to compile everything. And after 2014, Arch Linux actually compile everything with this Stack Protector Strong. Okay, so that's a little bit of evolution of this very simple idea canary. Then let's take a look what this IBM Properties does. So on the left-hand side, we have this program, which is just a function foo. It has 3 local variables, A, B, C, D. A is an integer, B is a pointer, C is an array of characters, D is another array of characters. Then there is a string copy to C, and this is where the buffer overflow could be. And also there's another string copy to D. So the stack layout we are familiar with. So far, we have seen that the stack layout of a program like this, we have a stack layout like this. We have a return address on the top, saved EBP, then A, B, C, D will be laid out in the order they are defined in the say function. Okay. Then the problem here is D can override C and everything above. C can override B, A, and everything above. With the canary, usually where we put canary? We put the canary after lower than save the EBP. So if we, for example, we just say that we put them EBP minus C, then all the variables, local variables will be lower than that. So even though return address, save the EBP is protected, the local variable A, B are not protected. So the IBM Properties is just one more thing. they will rearrange those local variables. In addition to put a canary there, it will rearrange the local variables. So they will put the dangerous ones like C, D directly under canary, then A, B will be even lower. So even if C, D can override, they override the canary, they cannot override A, B. So that is what IBM properly does. So I think I used some programs, or I tried to, I hacked some programs generated by properties before. That's why I remember I think the layout is a little bit different. So that's why usually when I say the C code, I don't really trust that is a layout. I have to see the binary code to disassembly to see what is the real layout. Okay, any questions so far?
Yes, out of curiosity, why didn't they just move the canary bit after the locals?
If you move that, what do you mean by after locals? After which locals? If you move that, let's say, if you move this one after C and D, then you cannot protect the return address, right? Make sense?
Yeah, that makes more sense. Okay.
Yeah.
You'd have to have a second canary bit or
Exactly.
do what they're doing. Yeah.
Exactly. You can have multiple, then the performance is a problem. Right? Yeah, but that's a good question. Probably if you don't ask that, someone may not think about that. Okay. Any other questions? Okay.
So, can you hear me?
No, it's like you are speaking like from distance.
Sorry, I have a weird setup now.
Okay.
I just wanted to ask if the registers like GS, like the thread storage, are those usually used for the purpose kind of that we see here? Like for instance, to do like a number comparison, but just making sure that the location of the copy of one of those is secure. Is
Exactly.
that normally how those are used?
So at least for Linux, at least for those two, like a 32-bit version and 64-bit version, GS and FS are specifically used for this purpose. They're specifically used to, it's not directly store the address of thread local storage, but more like indexed to an in-kernel data structure that eventually point to thread local storage. So this is like a convention. They do use this for this. Also, I have a link here. You can see the link here actually show you the data structure of the thread local storage. So you can see that this structure is a thread local storage. Then we have a pointer, and obviously for 64-bit version, this pointer is 64-bit. 32-bit version, this is 4 bytes. Then you can see one of those data here is a stack guard. That is a canary. And when a program is loaded, the GS is always point to this. Of course, I mean, the GS is a register, right? So for different process, for different thread, the GS could have a different value. When you run another thread, when you run another process, there will be a context switch. So yeah, so that answers your question. Yes, these are used to point to TRX. Any other questions? We're good? Okay, we are going to move to the next part, which is a lot of fun. Okay, so we are going to learn how to bypass canary, at least for some scenarios. So we're trying to bypass stack protector, this flag, but actually it works for OR and strong as well. So obviously, to bypass canaries, there are many different approaches we can use. The first one is, let's say if there is a information leakage vulnerability. If there is a read pointer somewhere you can control, then you can read whatever is in the memory. And if the calorie is stored on the stack, you can simply read it out. And then you can craft your exploit. And when you craft the exploit, you already know what the calorie is, then you cannot stop you. So format string vulnerability can help us do that if there is a format string vulnerability, but we haven't talked about that yet. We will cover that at the second half of the class as the semester. So that's not what we're going to talk about today. Then the next approach is, like always, we can just guess. We can just brute force. So for 62-bit version, we already know that the least significant byte is always 0. So technically, there are only 3 bytes of randomness. That's still like 16 million possibilities. For 64-bit version, obviously we have 7 bytes of randomness. So that's basically not crackable. But even for this one, for 3 bytes of randomness, 16 million combinations, if it takes us 1 second to guess a calorie, I did a calculation, we have to spend 190 days, at most 190 days to correctly guess the calorie. So obviously, this is not a good approach either. However, one of the problems I mentioned several times is when an application fork itself, the calorie will not be regenerated. The calorie is generated when the process is created. When the process fork itself, it makes another copy of itself, and the other copy will have the exactly same calorie. So the child process will not generate the new calorie, it will be the same. So if it doesn't generate the new calorie, do we still have to guess those 3 bytes at the same time? Actually, no, we don't have to. We can guess those byte by byte, okay? So if we guess those byte by byte, it's like, for example, we know the last byte is 0. We don't have to guess. The least significant byte is 0. We don't have to guess. Then let's say the least significant byte is a 0 byte, okay? 0 byte. Then the first byte, we can overwrite 2 bytes of the calorie, and we are going to guess the second byte. And how many combinations are there? It's just 1 byte. It's just 256 possibilities. Then we get the value. At most, we guess 256 guesses. Then we know the first 2 bytes. Then we try to overwrite the first 3 bytes, right? And we already know what the first 2 bytes are. Then for the third byte, we only need to guess another 256 times, right? So we only need to guess at most 706 times. That is how we can crack guess the byte. So I actually carefully designed this vulnerable function, and we're going to break this. So you may think this function, this application look a little bit weird. It may not represent real-world applications. That's actually not true. So a lot of real-world applications will use structures similar to this. So basically, they will fork themselves. For example, server applications, like web servers, like TCP servers. So they will use fork a lot. How many of you did any socket programming before? Anyone did socket programming before? Oh, so Phil did socket programming. Charles did socket programming. Okay. Okay, I don't know anyone else did socket programming. So when you do socket programming, what do? You usually have a you create a socket for TCP. You create a socket, then the server has a listen. Whenever there's a request, you have to you usually create another socket, right? After listen, you create another socket. Then if you only have one thread, what will happen? Your listening socket will be blocked. Your worker socket will take over. You don't want that. You want your listening socket to keep working. So you usually create a worker thread to take over. So your listening socket will just dispatching the request, and you have many worker thread to handle the actual to provide actual service. However, the problem with this is if you run everything in one process, everything are just a thread. If there's a vulnerability, it could crash your whole program. So another way to do this is instead of using threads, you fork yourself. You create another process. So even if the worker process is crashed, it's okay. Your main process, your listener process, they're still there. So a lot of web servers, TCP servers, they use a similar structure as this program. Then let's take a look at this program. We have a main function, and in this main function, we just have a big while loop. In this while loop, we will just do a fork. Fork is a system call. If you took operating system class before, probably the very first application, the first programming assignment you did in operating system class is probably developing a shell. And a shell will use fork to create other programs. Like if you want to type ls, the shell will actually fork itself, then call the system call exe to create a ls. Then it will be two process. So here's the same thing. So when we do fork, the fork will return to both the child process and the parent process. If the fork returns 0, it means we're in the child process. Otherwise, it's in the parent process. So in the child process, what we do is we just print out the child process process ID. Then we call the vulnerable function vulfoo. If the vulfoo returns, it will just print out I pt the foo. Then it will exit. So that's what the child process does. The child process will do this, then exit. Okay. And the parent process will print out its PID, then wait for the child process. So the parent process will block at here. If the child process exit, the parent will wake up from here, then go back to the while loop, create another child process, then go back here. So the child process, the parent process will always have its own, fixed PID. It's not changed, but there will be many child process created. Okay, then let's see what is this vulfoo function does. The vulfoo function has a buffer, 40 bytes in C code. Then there is a file. It's going to open a file. So what it does is this also has a big loop. It will try to open a local file called exploit. It will read that local file exploit. Imagine this is like, a child process taking data from the file system or taking data from TCP, from network. But the data it is taking, it's not necessarily benign data, could be malicious data. So if this exploit file doesn't exist, it will just, this is not a big while, sorry. It will just keep trying to open this file. Until after it opens, it will just sleep a little bit because if we don't sleep, we'll probably not get the data. Anyway, it will just read from this file 70 bytes, read 70 bytes from the file, then put that back to that buffer. And that buffer could be what? Could be overflowed, right? Could be overwritten. However, this program is protected by Canary, okay? Also, this program, this Overflow function will print out child process reads how many bytes and what is the canary we are guessing here. So I calculate where the canary is. Basically, the canary is at 40 bytes. That's where it is. I will show you in a minute why it's there. Then it will print out what is the canary we're guessing. Then the vulnerabilities here, we're going to do a memory copy. We're going to memory copy whatever we read from the file to this buffer to override this. Then it will close the file, remove this exploit, then return. So this is what it does. So let's say if this exploit is a benign one, there's like, let's say we put 10 bytes in. So what will happen? We put the 10 bytes in a local file called exploit. Then this program will read that 10 bytes, put in the buffer, then no buffer overflow. It's like nothing happened. It will return. After it returns, it will print out IP to the full, then exit. Then the parent will create another process for us. Okay, so this is what happens. So if the exploit is huge, it overrides the canary. What will happen? If this exploit is huge, it overrides the canary. Then what happens is this child process will print out that stack smashing detected and exit. Okay. Then when you exit, the parent will receive the message the child has exited. Then it will go back to the loop, create a new child for us. So this is how we are going to hack this program. So remember, the parent will create as many children as we want, but all of them are forked. So all of them will have the same canary, right? So our goal is to guess what that canary is. And eventually we want to get do another level of attack. We want to get the shell. So in this one, I actually make the stack executable. It doesn't have to, as long as we bypass the canary, we can do a return to libc. But just to make things a little bit easier, I make the stack executable. So we're going to put a share code onto the stack. Then we just try to return 0. So this is what I get from the disassembly. Let's go there. We go to bypass canary, and we just do an object done. BC, I think. I call it BC. Then we go to the function Overflow, just to prove you we are using canary here. So here is GS14. So canary is stored at EBP -C, and the buffer is at, there are so many things here. We just go to a memory copy. This is a memory set doesn't matter. Memory set is not the vulnerability. The memory copy is a vulnerability. Here's a memory copy, and we can say the parameter memory copy is EBP -34. Okay, so the distance between buffer and saved EBP is 52 bytes, and canary is at EBP -C. The buffer itself at C level is the distance between buffer and canary is, so it's 52. It's basically 34 minus C, right? This part is C. So that's 28 in hex, which is 40 bytes. Okay. So which means as long as, so it's the same as previous one. As long as we override more than 40 bytes, we're overriding canary. And we know the least significant byte of canary is 0. Okay. Any question here?
Quick question, Dr. Zhou.
Yeah.
What's going on with the remaining 8 bytes then above the canary? Because it's only 8 itself, right?
Yeah. it doesn't really matter. It doesn't really matter. It's like I think the purpose for this is kind of like alignment to make things a little bit faster. Yeah. Yeah. So
Great.
that one you can put garbage there. Doesn't really matter. Yeah.
Sure.
No one you saw the code. No one is reading it. No one is using it. Yeah. So yeah, go ahead.
Sorry, there like maybe 10 slides ago you explained that we only need 768 tries or something like that to guess the canary.
Yes.
I don't quite get why is it only 600 whatever. Yeah.
So that's exactly what we are going to do next, but let me explain a little bit.
Okay.
So let's say we have the canary. The canary is how many bytes? 4 bytes here, right? Technically it's 3 bytes because we know the least significant byte is 0. We don't need to guess that, right? So imagine how we're going to crack this. We're going to overwrite 41 bytes. And the 41th byte will be 0. Where that trigger the smash stack, where that trigger that stack smashing detected, where it were not, right? Because we didn't change the canary, did we? We didn't. We know the last byte is 0, and we're putting 0 there. It doesn't trigger that, right? Make sense?
Yes.
Then we're going to put 1 more byte there. So we're testing the second byte of the canary. Then we test from 0 to 255. So we're trying 256 times. We're not overwriting the higher 2 bytes of the canary. Make sense?
Yep.
So in this case, at most 256 times, we will find out what the second byte of the canary is. Right?
It makes sense now. Yeah.
Then we move to the third byte. So we're not guessing all of this at the same time. That's the key. That's the key. Yeah. So now we are going to do this demo. I developed a Python script to do this, and I'm going to show you the Python script, but I'm not going to share with you. So in the homework, you have to write your own script to crack this. Okay. So this is the first time in this class we're not only writing a Python command, we're writing a Python program to do the hacking. So first we need to disable AS. I think we did disable that. Let's say let's do GDB first to make sure we disable it. Yeah, I think I always disable this. Okay. Then let's put the share code there first to get everything ready. Let's put a share code there. Oops. What's the best way for me to do this? I mean, just copy it here. Yeah. I hope there's no weird characters here. Okay, looks good. Okay. Yeah, now we should have it. Do we have a share code there? Yeah, we have the share code there. How big starts that there? 500 should be good. Then we're going to write a script to guess the canary byte by byte. So at this side, let me just run the program first. Let me have another terminal. Go to the same folder. We have an exploit file. So remember, it looks for a local file called exploit. We don't have that file at this moment. This is a Python code to generate that file. Then we can run this program, BC. So now we have this program. The program will keep searching the local folder for that file. And the parent PID is this, the child PID is this. Okay, then let's just do something. Let's do a Python let's just do this for 10. So we put we output this to exploit, right? So this will generate the local exploit file. Then this side will read it, and this one will not generate any overflow. So this could be 10 bytes, or it could be, it should be 10 bytes. It will not append any new lines there, right? Were it? I'm not sure. Maybe it will append a new line there to make it 11 bytes. We will figure out here. So let's create this. Then this side, oh yeah, it does append that, a new line there. So this side, it reads 11 bytes from the file, and there is no buffer overflow, right? So it says I paid the full. Then you can see that the parent PID is not changed. The parent is not changed. The child will create a new child process and keep listening. It's kind of like keep listening. Then let's do 40. When we do 40, it's actually 40. Let's do something bigger. Let's do 60, right? Then this one obviously will trigger the buffer overflow of the child. Note that the parent will never have the buffer overflow here. The parent doesn't call the val foo, okay? The parent just creates the child. The child will have this val foo, okay? So back here, then we create this, then child will read this, and the child should have a buffer overflow, okay? See? So now we do this, then the child will have a buffer overflow. It reads 61 bytes, and because we put A there, so it thinks the canary we're guessing is all A's, and it detects stack overflow. So the child is aborted, then the parent will create a new child. So this is how we are going to crack this, okay? So any idea how do we do this? Obviously we cannot do this. There's a lot of problem with this actually. So if we do, let's say we do 40, then we do this. Okay, will this be buffer overflow detected or not?
Not. Well, I know actually it's mem copy. Oh, right.
Yes, but it will be. It will be. The reason is when I do this, the share will append a new line after this. So it will be 0, 0, and also 0A after this. That's why when I do 60 here, it reads 61 bytes. See, the 1 byte is a new line character appended by the share. Yeah.
Quick question.
Yeah.
Why does is child process removing exploit when it's done?
Yes. The child process will remove it. Here, this is the code. The child process will remove it. And so what we can do with our program is we can write a Python program. It can be any program, right? Then that program will write 41 bytes there. Why is 41 bytes? First, the 40 bytes to cover the buffer. The value doesn't really matter. 1 byte to cover 0, 0 as the least significant byte of the canary. Then it's 42 bytes. Then we guess the second bytes. Then we guess from 0, 0 to what? To 255. Then we keep looking at the output here. If the output says stack smashing detected, which means that's not the right guess. If it says I PT the full, it actually means that is the right guess. Make sense?
Yep.
Okay. So that's what my program looked like. Let's say probably should do max. Probably need to change things a little bit. Okay. So this is my program to generate this exploit. It's very simple. We have a main function. In the main function, we have a big loop. We have a 1 byte ranging from 0 to 255. We try to check if the exploit file already exists. If it exists, we just sleep. Give the child an opportunity to remove it. Make sense? The child will read it to remove it. Okay. Then after, when we reach here, it means this file doesn't exist. Then we create a new file called exploit. Then we're going to overwrite this. Okay, first we write 40 bytes of garbage, doesn't matter. Then we write 1 byte of 0. Then we write 1 byte of those from 0 to 255. Then we close this file. And this one will not append any new lines in. Okay, does this make sense to you? Does the code make sense to you?
Yes, it does.
Okay, now we are, let's say we have any exploit here. We don't have any exploit here. Then we are going to run this exploit. Then let's see what's going on. So you can see on the left-hand side, we're starting guessing the Calorie. Now we're guessing 8, 9, 8. So if it prints out IP to the full, it means we actually hit the right byte there. And this will take up to 256 times, which is, I'm guessing, at least 3 minute, a second. So it's kind of like what? How many minutes is that?
5.
No.
300 seconds, you said, or?
So 1 second is 3. The total, one second we guess 3 times, and we're guessing 256, right? So it's like 80, so 1 minute, 1.5 minutes. Yeah. So at most 1.5 minutes, we should be able to say IP to the full, right? So when we say IP to the full, that's when we get the correct value.
I think we already have it.
Yeah, by the way, I don't know what the Calorie is, like you, I don't know, right? Because you saw me started the program BC, and the Calorie was generated that time. I don't know what the Calorie is. Of course, later I will show you how we can cheat, but that's because I'm doing everything on my local computer, so we can cheat. Yeah. So right now.
So did you see the answer? Did you see that it says IP to the full?
Yeah, it's way up.
Oh, really? You saw that?
Yeah. Yeah, I saw how.
Where?
I mean, we're looking. Let's see. In the. Gosh, I wish I would have put it in my head what the suffix was. I watched it travel up the screen though.
Sure, I can say it.
Oh wait, go up a little. I think I saw. Yeah, right there. Wait, go down a little now. Maybe we could just copy the entire thing and just grab or.
Oh really? I didn't. Okay, let's see.
Yeah, I said something right when I saw it, and then it escaped me to think to index it.
I should change the program a little bit to make it more obvious. Yeah. Just let me know if you see it. I'm moving.
Right there.
Yeah, right there.
3B00. So 3B.
3B. Yeah, I should change this to make it. So now we don't close this program, right? We don't close this program. If we close this program, we restart it, it will be a new Calorie, right? So what we do is we just stop here, right? And when we stop here, this part stops. Then what we can do? We change this script. The reason I change this script is because this script cannot monitor the status of this one to detect if it's crashed. It's crashing. So now we do it's 3B, right? So we do 3B. Okay. So let's verify this. So if we do 3B this, it should not generate trigger buffer overflow. Make sense? When we do this, it should be, yeah. When we do this, it should be PT to full. Let's try it again. See? IP to the full, right? So which means this is correct. Then we're going to guess the third byte. So now it gets the third byte. So we have a 1, 2, and third byte. Now it gets the third byte. What I'm missing here? Oh, this one. This one. Now it gets a third byte. Okay. At most 1.5 minutes, we will get it. The second byte is 3B, the third byte right now is 12. I can make it a little bit faster, but I find out that if I do not sleep there, sometimes it doesn't read anything. It opens the file, but it doesn't read. Some file system problem, that's why I couldn't sleep there. Because of that, it's a little bit slower. We're halfway, almost halfway there when we hit 7F. Okay, we're not lucky this time. This is where you get leverage to think about, oh, did I make any problem? Did I have any problem in my script? It's already halfway. We're really that unlucky, or
Be like the last one.
Yeah, let's go FF. Who's taking
Yeah.
that?
It's for dramatic effect.
Oh yeah,
Mark.
do you see it?
Yeah.
I see it. Here. It's E7. Yep. We're not lucky there. Okay. But we are close. Now we know the one is E7. E7. Okay, let's verify it again. Yep, E7 is good. Okay, 1 byte to go. Now we change this back this. That's correct. 1 more byte to go.
Early one.
It's right there.
You found it?
Yeah.
Oh, here. No, that's the first one. E7? Oh, where is it? Do you see it? I don't.
The only other thing I can think of is maybe the screen lapped over itself when.
Yeah, it could be. Yeah. It could be the E7, right? Yeah, I don't see it.
Yeah, might have false positive, I guess.
Can we check again though? I think we saw it.
Okay, let's check from the beginning. Starting from here. That's E7, and here's where we start guessing. So all of this.
0-7. It's
Oh,
0-7.
Yeah, it's here. Yeah, Phil was correct. Yeah, it's 0-7. Yeah, it's 0-7. Okay.
I think we caught that. That would have been pretty bad.
Yeah. So this one is easy. So now we have 0-7. Okay. Then this part we don't need this part anymore. So now we have our let's verify this again. So this one should always repeat the full. Yep. Okay. Now we have this one. Do we know the address of the? Did we? I think we forgot to get the address of our share code, right? Can we get here? It's not here, is it? Not in this one. It's only in this one. Huh, this is a problem. How can we get the address of share code?
I think you can probably do it in the other one too, because you have 500.
Yeah, we just
you can just
get a random guess, right?
Yeah.
Yeah. Let's just get anyone here. Let's get this one. Then let's just do user. So this is the address we're going to guess.
If you also scroll in your left terminal up all the way, you can see where they like to the very up, because you printed, and you can see what it's located next.
Yeah, it's next to this one. So which one is higher address? I'm a little bit confused. This one should be higher address, right? This one should be lower. I think so.
Or plus minus probably.
Yeah, maybe let's try this one. Let's try this one. So this is the address somewhere from here. Maybe add like 500 or something. That's where we're going to guess this address. Then DVOA. Then we go back to create our share code. Then what is our address again? So we know the canary, and the canary is only 4 bytes, but there is another, like Phil said, there's another 8 bytes of garbage. Then another 4 bytes of EBP, and we're going to have the return address. Right? So then 12 bytes in total. So then we just add 12 bytes of A there. 12 bytes of A. Then we add the return address, which is 4 bytes, and we have OABB. OABB.
Does the space for the canary count into that 12 bytes?
No.
Okay.
The canary is 4 bytes itself. Then it has 8 bytes between the saved EBP. Between the saved EBP, right?
Okay. Oh, that's right. Yeah, I forgot about the.
Yeah.
I forgot about the saved. That's right.
Yeah, the saved it. Then let's say, DDOA. So that's DDOA somewhere there. DDOA, if we want to plus, let's make it a D, make it EOA, something like this. And then we are going to send this. And we're going to then we send out this message to car. See, nope. Why we're putting 60
I think
bucks?
you did a lot. No, actually, no. Not.
Why is 60 bucks here? Which part? So this is 40 bytes, 4 bytes canary, 12 bytes. Then looks correct to me, and it's not showing I pity the fool, and it's not showing detect smash the stack detector.
I think
the child did crash, right? No, not necessarily. The child probably deletes that one. Yeah, go ahead. What do you want to say?
maybe instead of DE, because the other one is very small jump. Oh, I would maybe try instead of DD, I would try put DD, and I would maybe instead of A, I would try maybe what F.
FA.
Oh yes, F8 should work. Yeah, okay.
Let's try. Nope.
No.
Well, hey, Beck, you should write a program that iterates your shell address in memory space too, so you don't have to do any of this anymore.
Yeah, maybe we could go lower, because I don't know if we maybe instead of AF we do minus instead.
Okay, let's do. So this is already 0 here. Let's go DC.
Yeah.
Okay. Yeah, I'm not sure how they are arranged there. Oh,
yeah.
We hit it.
That's the one.
That's it. We got it. Yeah. So that's how we crack this program. Yeah. So you see, even though I'm running everything on my local computer, this is actually similar to what you attack a remote server, right? It's like you're sending out a TCP message or whatever to do that. Okay, now I'm going to just cheat a little bit to show you that we can actually, because everything went down on my local machine, so we can just use GDB to attach to this child here.
I have a question.
Yeah.
How could this technique be used in, real life? Like, two windows like this, waiting for a child process, etc. I know you said that's not exactly common in the real world, but how would you apply this technique in the real world?
In real world, what could happen is you have a web server. The web server will fork a lot of a worker process, not a thread, worker process. And they will have the exactly same canary. So you can keep sending out those, we can call it probes, to try to hack it. And eventually you can trigger, you can guess the canary and bypass the canary to override the return address. Those web servers, usually they are set UID programs. So they have the root privilege. So if you are able to run arbitrary code in the worker process, it means you have the root privilege. You take full control over the computer and do whatever you want. Yeah. Make sense?
Yeah. So when you crash, let's say a child worker you interact with, I suppose you would know that you maybe crashed or didn't crash it based on like if it timed out or gave you a response, right? Yeah.
Somehow there is some kind of an indicator. You know what's going on. Yeah.
Okay.
That's what you need. Yeah. Okay. Go back here. So the child. That's why I print out the child process, the PID here, so we can cheat a little bit. So let's attach our GDB to this child process 5936. Did we attach it? Oh no, we need a pseudo to attach it. Okay, so now we attach to this process the child process. It doesn't really matter which child or the all the parents. We just want to check if our guess of the Canary is corrected. Now we do this, then we do this address plus what? 14, right? So the value we're expecting is at 7E07 whatever. Oop, probably a little bit off. What's going on?
Why is address 64-bit?
Yeah, why 64-bit? Which one we're running?
I think you might have attached to the shell somehow, and the shell is 64.
Oh yeah. We cannot. Oh yeah, you're right. Because we create a new shell. Remember? So this child process is not that process anymore. It's a yeah. Instead let's attach to the parent, which is 224200. Anyway, it will be the same. So we do, yeah, you're right. Because we're running a 64-bit shell there. So when we test to it, it's not that 32-bit child anymore. That's the 64-bit of shell. Now, then we do this.
Do you know? Do you know what kind of like what system call or whatever is used to like spawn a new process and give it? It's not fork, right? Like when you create a shell, like how do you pass it your process ID and you?
The process ID is not changed there. So anyway, at first let's verify this is our canary. That's correct, right? We correctly guessed this one. I have an idea. Let's just attach to that 64-bit. This is a 64-bit, right? Let's do 28. No, not working. Let's see. Why did the address? Oh, okay. Yeah, that's not the address I want. This is the address. Let's do 28. So it's a different one. Yeah. Okay. So this doesn't work. So here we have two processes. One is parent, one is child. Then the 32-bit child is replaced with this 64-bit of share here. And the PID is not changed because we didn't fork. We didn't create a new process. We just replaced it.
Okay, and we replaced it, and when we replace it, we also do we pass it our PID to that process or?
It's not like you pass the PID to the process. It's like it keeps it. Yeah, it's not really passed to it. Let's do a grep sh. So let's see. Why do I have so many here?
What if we write like maybe run the exploit again? Did it spawn a new process or did it like actually no, never mind.
Hold on. Let me do what do we have? So what is sh in sh here? No, this is not the one. It's dash. Dash. No. Yeah, I'm not sure. I don't think we have a new PID. But I need to verify that. I don't think we have a new PID. Let's grab this one. Instead of grabbing 2936, right? Grab this one. So, yeah, see? It doesn't have a new PID. So the child was at BC. Now it's SH, and it has the same PID here. It's just replaced. The PID is not like, its PID is kind of like the PID is stored in the kernel, right? It's not associated with, it's not stored with the app. So it's not like the app passed it to a new app. for the app itself to get the PID, it has to make a system call. That's why you have to use get PID, which is a system call, section 2.
Okay.
So, yeah. So it has to call the kernel to ask the kernel to tell itself what is my PID. Yeah. It doesn't really store that in its own address space anyway. Yeah.
So are we completely losing I guess the memory layout of the child process? Like when it runs sh, does it, I guess the 32-bit version of memory gets thrown away?
That's a very good question. That's very complicated. The kernel use a lot of tricks to make sure when you create a new process, when you execute a new program, everything is as fast as possible. So, for example, you have a program running and a program fork itself. What you imagine is the new program will have exactly the same copy of the old program, so there will be 2 copies, right? That's what you think. You think they should have 2 copies. But what the kernel does is it will not make 2 copies. The 2 programs will share a lot of things. Physically, a lot of things are just 1 copy. Until the new program will make changes to, for example, let's share some memory pages. Until the new program will make changes to those shared memory pages, the kernel will create another copy for it so it can change. Then they will have 2 different copies. So that's something called copy on write. There are a lot of techniques like that to make things run faster. So when you say, do we lost everything? I'm not sure it's everything. For example, yeah, I don't think it's everything. Yeah.
Okay, got it. Thank you.
Mm-hmm. Okay, any other questions? Okay, I don't have any other slides actually. That's exactly what we're going to talk about today. So next week, there are several other topics regarding protection of buffer overflow. For example, we will talk about what if we give up preventing this buffer overflow. What can we do? We can set up a sandbox. So even if the program is compromised, it can only do certain things because we built a sandbox around it. And one of the sandbox is called the seccomp. It's like a firewall. It's like a system called firewall. It makes sure that a program can only make certain system calls. It cannot make, for example, it cannot create a new process. We can define something like that. So even if you can run your shellcode is basically making system calls. Even if you can run shellcode, we make sure that the kernel will just stop you from doing that. That's one of them. And also, what else we're talking about? We're talking about, well, next week I plan to cover the GOT PRT part, which can be, so it's related to that relocation protection there. So that's what we're going to cover next week. Which one? Let's forget about this. Yeah, so we're talking about this one next week. And also the PIE part, I plan to cover that after address space layout randomization. So there we will cover code, partition dependent code, CFI, system return to libc 64-bit version, and ROP. So ROP is a very exciting one, but well, what we're doing so far is also very exciting. Okay, any other questions? Okay, so I guess that's all for today. I'm going to, one of the homework for you guys is to do this attempt. you need to write your own script. If your script can be, so my script is like semi-automatic. If your script can be fully automatic, then you can get some extra points. Think about how to make this fully automated. Okay. You probably can get from this standard out of this program. You have the, yeah, it's tricky because the PID is changing. Anyway, think about it. If you can make it fully automated, you get some extra point for it. Okay. Cool.
Dr. Jack, are we able to modify the source code for the target program at all, or does that have to stay the same?
What do you want to modify?
I was thinking about having it dump another text file to make two-way communication between the two programs, but that might be too much.
Two-way communication of what program?
Yeah. This is me. I'm prototyping in my head, so I'm going to have a hard time describing my idea. But it would be me adjusting a lot.
No, I don't want you to do that because this is a target program, right? You are not supposed to change the target program.
That's why I asked.
Yeah.
I'm wondering if is it possible to somehow get the Python to know the PID of the child process if it knows that, to know how it exited, if there was like a stack through PID.
You probably can use the proc file system. From there you can get because the parent PID doesn't change, right? You can easily find the parent. Then from there you probably can find the child, then get the status there.
Yeah.
Or anyway, you're running on your own computer, so you have sudo, so you probably can hook some signals there. That's possible too. Yeah.
Okay.
It's definitely doable. Just you have to make a lot of changes to the original exploit, I think. Yeah, my exploit is like only 5-6 lines, but it's a semi-automatic. To make it fully automatic, I assume a lot of work has to be done there. Okay, good. Okay, see you guys next week. Okay, bye.
See you.
See you, Professor.